Hi there, folks. Today we're looking at parallel and perpendicular lines. More specifically, we're looking at kind of the relationship between parallel and perpendicular lines and some of the theorems and stuff that relates some of those things together. Okay, so when we have parallel lines, what does that tell us about other parallel lines? Or what if we have perpendicular lines? What does that tell us about whether or not lines are parallel? That kind of stuff. All right. So coming to these ins and outs of these relationships. So the first one we're going to look at is the third line parallel theorem. So basically what I have here is Q and M are parallel lines, all right? But I also have that Q and P are parallel lines, and I want to prove that M is parallel to P, all right? And this can be kind of done in a multitude of ways. I could have said that, Q and M are parallel and M and P are parallel and prove that P and Q are parallel, okay? But basically I have two of these lines parallel, and I want to prove that the third set is also parallel, okay? And when you're looking at this, you might think it's obvious, and you might say, well, isn't that kind of like our transitive property? Well, yeah, this theorem is similar to the transitive property, but the question is, how do we prove it? All right? And the issue here is, as I look at the picture and I look at what's given, you might try to start this proof and go, well, I don't have anything else. There's nothing else shown here that I can go off of, all right? And this introduces something new that we're going to have with proofs, and that's the idea of adding to the picture. Okay, there are certain things that we are allowed to add to a picture. One of the things that we sometimes do in geometry are constructions. We didn't do any of those, but there are certain things you can construct. Like using a straight edge, you can draw a line, all right? And it is a perfect line because it's nice and straight, okay, that kind of stuff, all right? You can draw a parallel line. You can construct a line that's parallel. So we can add something to this picture and state what we have added. For example, for this one, the thing I really need here is I need some kind of transversal, all right? So right here, let me draw a transversal. I'm going to do it in green. Boom, I just drew a transversal. Pretty awesome, right? So I added a transversal to the picture because, frankly, I just don't have enough stuff to use right now. It's hard to construct a proof when I don't have anything that I can, label or reference to in terms of this picture. And then I'm going to go a step further. I'm going to label the angles I created as 1, 2, and 3. And notice I only labeled those angles, and that's okay. I don't need to label any other angles. I could label other angles if I wanted to, all right? But I just added to the picture, all right? And here's what we do in terms of the statements and the reasons. I'm going to say what I did as part of my statements. I'm going to tell everyone that as part of this proof, I added a line. I added a transversal to this thing, okay? So here we go. Step 1, Q is parallel to M, and Q is parallel to P. All right, I know that because it was given, so once again, I always state my given first. All right, even if I'm not using all of the stuff right away, I state the given first. And then the next thing I did, well, I already did it, all right, but I have to justify it down here. I have to say, hey, down here, and I should label this guy. I'll call that line L. So I created line L. I made a transversal. So I'm just going to say something like, line L is a transversal. And I know that because I'm the one who drew it. I made that line. All right. I am the creator. All right. So I'm just going to say I constructed it, or all right. I added it to the picture. Okay. I created it, and I created it such that it was a transversal. I drew it that way. Why is it a transversal? Because I made it so. All right. And so now I have lots of other things that I can reference in this picture. Okay. And the first thing I might do is say, well, if Q and M are parallel, I know something about those angles, don't I? Yeah, I know that angle 1 is congruent to angle 2. I also know that Q and P, that those lines are parallel. So guess what? In that same vein, I know that angle 1 is congruent to angle 3. Okay? And I know that because that's my corresponding angles theorem. And even though I'm talking about two separate lines, it's still the same justification. Like if I was trying to say that 1 is congruent to 2, that's because the lines are parallel and corresponding angles are congruent. All right. If I was trying to say that 1 is congruent to 3, it's the same reason. It's because the lines are parallel and, corresponding angles are congruent. Okay. So it's the same justification, which is why I write it in the same step. Corresponding angles are congruent when lines are parallel. Okay? And that is a terrible looking congruent sign. I'm ashamed of it, and I'm going to redraw it because I can't live with that. Whew, much better. Totally a congruent sign now. Okay? But now from here, think about what I just stated. All right? And maybe I'll read a little bit backwards again. Angle 2 is congruent to angle 1. Angle 1 is congruent to the angle 3. Therefore, right? Yeah, we all know where you're going with this, Mr. Jansen. Angle 2 is congruent to angle 3. But blam! And why do I know that? Well, it's basically my transitive property. Okay? And now from here, I know that 2 and 3 are congruent. What does that tell me about the lines? All right? See, 2 and 3 are corresponding angles. I know they're corresponding angles because I constructed that sweet transversal earlier. It was pretty awesome. All right? But if I have the situation, I have two lines cut by a transversal, the corresponding angles are congruent, that tells me that the lines are parallel. Okay? And that's one of those converse theorems we were looking at. These are parallel because, again, if corresponding angles congruent, oh, I got a little green dash in there somehow, then stuff is parallel. Nailed it. Okay? And 5 steps seems ridiculous for something that seems so obvious to us from the beginning, that if these guys are parallel and these guys are parallel, well then of course all 3 of them are parallel. Okay? All 3 of them are parallel to one another. All right? But now we know that. Now it's part of our toolkit. Now we can use that whenever we want. All right? So, third line parallel theorem. 2 lines are parallel to the same line, then the lines are parallel. All right? The next 2 theorems, we're kind of going to do this a little different. Instead of doing a 2-column proof, we've been doing a lot of those, we're going to kind of do this one as almost like a paragraph proof. All right? A paragraph proof is kind of the same deal. We still want to go through that progression, but we kind of just state it as like a story. All right? We literally write a paragraph and say, I know this because of this. Then I know this because of this. Then I know this because of this. And then, all right? So instead of doing it as kind of this 2-column, this and this, I just kind of tell it like a story. Okay? So explain how you know that M is parallel to N. So when I look at the picture, I see the transversal T. I see some little red boxes, which means I have some perpendicular lines. All right. So what I see in the picture, all right, I just kind of state this. I say, in my paragraph, I would say that T is perpendicular to M, and N is perpendicular. T is perpendicular to N, or N is perpendicular to T, okay? And that's given, all right? And I could say in my paragraph, given, or I could maybe start with, it's given, that T is, okay? But again, we're just telling it like a story. I can see that from the picture, all right? The symbols told me so. Those are perpendicular. But now think about what that means. All right, perpendicular means that I have a right angle, and maybe I want to label these. I'm going to call this angle 1 and angle 2. Oh, so I could say, well, I know that angle 1 and angle 2 are right angles because that's what perpendicular means, or maybe because I'm going to abbreviate this a little more, sorry. Because the definition of perpendicular angle says so, okay? That's what perpendicular lines, perpendicular lines means I have right angles, okay? Well, then I automatically know that angle 1 is congruent to angle 2. And that was one of those theorems that we just talked about. We didn't actually do a proof for. Remember, all right angles have the same measurement, so all right angles are congruent. So 1 and 2 are congruent because they're both right angles. Maybe you want to do like this, like little abbreviation for because all right angles are congruent. And now look at what I have. I have corresponding angles congruent. That means the lines are parallel. M is parallel to N because corresponding angles are congruent. And again, it's still the same thing that we would do in a 2-column proof, but instead of saying this is given, this is the statement, this is the reason, this is the statement, this, we tell it like a story. Say, hey, this happens because of this. And then this other thing we know because of this thing. And then, all right, but again, this is one that seems obvious. If I have a transversal that's perpendicular to two lines, well, then those lines are parallel. All right, for obvious reasons. Perpendicular gives me right angles. Right angles are the same no matter what, so corresponding angles are now congruent. All right, the lines are parallel. If I look at something like this guy, kind of using it in a little bit of a different way, this time it shows me the lines are parallel. It shows me that T and M are perpendicular, and I want to show that T is perpendicular to N as well. All right, so again, if I'm kind of doing this like a paragraph, I might say, it's given that M is parallel to N, and T is perpendicular to M. Okay, so I still start with what's given. I'm just stating, hey, this is what I see, but I do it like a sentence instead of like this and this. All right, and then I go from there. I say, okay, well, if I know these things are parallel, and once again, I'm going to label the picture because it makes life easy for me. See, I know that angles 1 and 2 are congruent, so maybe I'd say angle 1 is congruent to angle 2. And it's just warming up us to the idea of paragraph proofs, okay? And paragraph proofs are more like what you would do in like a courtroom if you were arguing, all right? You wouldn't hold up a piece of paper and say, okay, here's my columns. Step 1, I know this because of this. Now, you would state it kind of in a sentence type of format. But anyway, angle 1 is congruent to angle 2 because corresponding angles of parallel lines are congruent. Okay? And see, I also know that angle 1 is a right angle. And I know that, sorry, I'm going to use my abbreviation. I know that because of the definition of perpendicular lines. And here's the thing, I could switch those two sentences. I could have stated that was a right angle first. All right, it doesn't matter. The two things don't give us one another, so the order there doesn't really matter. But now, because I have those two things, I can say that angle 2 is also a right angle. Okay? See, I know angles 1 and 2 are congruent. I know that 1 is a right angle, therefore 2 has to be right angle as well. Okay? And again, we didn't necessarily talk about a theorem that says that. We're kind of using the converse of the theorem we already know. We know that all right angles are congruent. So if I have two angles that are congruent, one of them's a right angle, the other one has to be a right angle, okay? So it's kind of the same thing, but in reverse. But again, I think in terms of making a valid argument, which is the whole idea of why we're doing proofs, okay, you have a reasonable justification here. So angle 2 is a right angle. And I'm just going to say because it is congruent to a right angle. Okay? And then from here, if I know that angle 2 is a right angle, now I know the lines are perpendicular because that's what it means to be perpendicular, all right? So T is perpendicular to N, and that's because that's what it means, all right? That's the definition of perpendicular lines. Okay? But here's the idea. Instead of having the two columns, and me personally, I think 2-column proofs are easier, okay? But paragraph proofs are more practical, okay? When you're making constructing an argument to try to prove something, you are typically going to do it in this format, all right? And whether you're doing this for a mathematical concept or whether you're doing it to prove someone's innocence in the courtroom, all right? That's the one of the easiest examples I can think of, all right? Whether you're trying to win an argument with your brother or sister, all right? This is the logical progression that you want to go through, okay? So in a plane, if two lines are perpendicular to the same line, then the lines are parallel, all right? That was the first thing we just talked about. The second one, in a plane, if a line is perpendicular to one of two parallel lines, then it's got to be perpendicular to the other line. And again, these are in the same vein as the third line parallel theorem, but they're relating perpendicular lines, okay? We're still using 3 lines, but instead of 3 lines that are all parallel, we're using perpendicular lines to show things are parallel, okay? Or using parallel lines to show something else is perpendicular, okay? And again, now that we've proven it, all right, we'll count that as a paragraph proof. All right, now that we've proven it, it's added to our toolkit. We don't have to prove it again. We can use it, all right, to our benefit. Let's take a look at something like this. A couple real world examples, all right? If you've ever done any kind of construction, that's where the examples we're about to do come from. And there are other examples out there, all right? I just chose something like this because it's a nice visual. But when we look at something like this, students always look at this like with weird eyes at me. They're like, what in the world is that thing you have drawn? And what is a truss, Mr. Jansen? I think you misspelled the word trust, okay? It says an end truss. Oh, Mr. Jansen, it's supposed to be T-R-U-S-T. It's trust. No, truss. All right. The thing under your roof. See, there's a, you see like shingles or a metal roof. Okay. The thing that holds that up, all right, is things that I have pictured here. Okay. And the one on the end looks like this. It uses these kind of vertical pieces so that you can put siding up there and stuff. All right. Trust me. That's what's underneath your roof. If you were to crawl up in your attic, you would see these things at the end of your roof. You'd see one of these holding up your roof, okay? So an end truss for a roof is depicted above. If each vertical support is set at a right angle to the bottom support, what does that tell us about the vertical supports? So in other words, it's saying, hey, if this is a right angle, if this is a right angle, if this is the right angle, if all of these are perfectly vertical, if they're all right angle, what does that tell us about the supports? Okay, well, hopefully you're looking at it saying, well, it tells us that the supports are all parallel. Okay. And you're probably going, okay, well, yeah, that was obvious, but what does that matter? Who cares? Okay. This is why that's important. If I kind of zoom in on the thing, ready? It says if the roof has a 30-degree pitch, at what angle should the first vertical support be cut? And if you don't know what pitch is, the pitch is kind of how steep the roof is. So we're going to say that this is 30 degrees right here. This angle is 30 degrees, okay? And so what's happening here is if I kind of look at this, all right, from the perspective of, all right, all of these are 30 degrees. Well, think about it this way. Think about a transversal going across here, right? And so here's the thing. If I were to draw a line that's parallel, let me get my line tool out. So let me draw a line that's parallel to that original. There we go. That line's parallel to the bottom. So right here, I'm saying that this line is parallel to like this line right here. Okay? So if that's 30 degrees, and maybe I should have scooted that guy up just a little bit, just a wee bit, it means that guess what? This guy right here is also 30 degrees. Okay? So I'm creating these angles. This one is 30 degrees. This one is 30 degrees. And I know that because I already said that these lines were parallel, but these guys are also parallel. So this is 90 degrees. This is 90 degrees. So now think about this entire angle. This entire angle right here is 120 degrees. And that's my angle addition postulate. So we're kind of rolling all of these things into one. But now when you look at something like this, here's why that's important. So the angle that's actually on this piece of wood right here, so if we look at this angle right here, all right, that angle that I just drew in purple, that is a 120 degree angle. We just stated it, okay? If you were actually working on a construction site, you'd probably use a miter saw to cut this thing, and you would use the 30 degree angle. See, miter saws at 90 degrees cutting across is marked as 0. So they're measuring from 90 degrees, okay? So 30 degrees on a miter saw. So let's say I'm working construction. Now I know to cut that thing at 30 degrees. But what about the next one? What about the next vertical support? What angle should I cut it at? Will each vertical support be cut at the same angle as the first? And the answer is why. All right? See, this is important because I know I just figured out I got to cut the first one at 30 degrees. Well, what about the next one? Well, yeah, the next one I'm going to cut the same. So the answer here is yes. But why? Why should I cut them all the same? Because these are parallel lines. If I know all these trusses or all these truss supports are parallel, if this guy and this guy are parallel and this guy's parallel and this guy's parallel, it means that all of them are going to have the same angle. We're talking about corresponding angles. This is how that thing is used. Okay? And so the answer is yes. And the reason is because the lines are parallel. Okay? This is how some of this stuff is used in a real world application. And so what's nice about something like this, and people in construction do this all the time, they get one measurement, okay? They set the tool up so that it cuts that one measurement, so that it uses that one measurement, and now they use that as a template for the rest of what they do, okay? Instead of measuring it each time, they had to measure once, and now they can make all those cuts. And you see how that's faster and more efficient in terms of building something, okay?